Good morning, all of you. Respected chair and co-chair of this plenary session, and all the dignitaries. It's my pleasure to introduce the chair of today's very important plenary session, Dr. Kaushik Majumdar. I'm sorry. And I also welcome Dr. Raj Hosla, who is the speaker of this plenary session. Thank you, sir, for joining us online. And Dr. Kaushik Majumdar is presently the Director General, African Plant Nutrition Institute, Morocco. And he was the Vice President of the IPNI, coordinating the research and outreach activities of IPNI in Asia and Africa. Dr. Majumdar has a PhD in soil science, soil mineralogy and soil chemistry from USA, and his current area of interest is precision crop nutrition for climate resilience and soil health in smallholder production systems, and how that translates into production of sufficient and high quality diet for enhanced human health outcomes. Dr. Majumdar has contributed to the development of several site-specific fertilizer decision support tools, technical bulletins and training aids on sustainable plant nutrition, and has authored over 80 peer-reviewed scientific publications. Thank you for chairing this session, sir. Now, it's also my pleasure to introduce the co-chair of this session, Dr. Adrian Singh. He is NISA honorary scientist and worked in PAU Louisiana. He completed his MSc in 1971 from Punjab Agricultural University, then PhD in 1985 from Canada, and he was formerly head of Department of Soil Science at PAU Louisiana and consultant for many organizations including CIMI, IRRI and VISA. He is awarded with various fellowships including FNA, Fellow of National Academy of Agricultural Sciences, Fellow of Indian Society of Soil Science, and Fellow of Punjab Academy of Sciences. He is also bestowed with a number of awards, to name a few include the ICAR Rafi Ahmad Kidwai Award, Memorial Award, the FAI Silver Jubilee Award, the FAI Golden Jubilee Award twice, and Dr. G.S. Bush Distinguished Professor Award, European Union Fellowship Award, and he has implemented several projects during his long career funded by several national and international organizations, and also served as a member of several national and international committees, including Inspire, RSC, and he was a member of various ICAR institutes. And he has published more than 350 research papers, books, and bulletins, book chapters, and so on. So thank you very much for considering this session. I now request the chair to conduct the proceedings.
Thank you very much, and good morning to all of you. You have something to introduce to our speaker today is Professor Raj Hosla. He is a globally recognized authority of precision agriculture. He has been engaged in precision agriculture since inception and has made significant contributions in the development and spread of precision agriculture worldwide. Most recently, he served as a member of he is a founder and past president of the International Society of Precision Agriculture. Most recently, he served as a member of National Academy of Science Executive Committee on Science Breakthrough 2030. In 2017, his research was recognized with the Warner L. Nelson Award for Diagnosis of E-Limiting Factors Award by the American Society of Agronomy. Previously, he has been recognized as a Precision Ag Educator of the Year 2015 by the U.S. agricultural industry. In 2012, Dr. Hosla was made the Jefferson Science Fellow by the National Academy of Sciences and was appointed as a Senior Science Advisor on Food Security, the U.S. Department of State. In 2011, he was inducted by NASA, the U.S. Presidential Advisory Board on Positioning, Navigation, and Timing, to work on the U.S. space-based GPS policy. Professor Hosla is a Fellow of American Society of Agronomy, Soil Science Society of America, Soil and Water Conservation Society, and Honorary Life Medman Fellow of International Society of Precision Agriculture. Professor Hosla's research specializes in harnessing spatial and temporal heterogeneity in managed agro-ecosystem and translating those into better decision models. His group has extensively used remote sensing and other geospatial tools to enhance production, resource use efficiency, profitability, and sustainability of managed agro-ecosystem. Their ongoing precision nitrogen management work has demonstrated significant reductions in nitrous oxide emissions on farm fields. Most recently, his laboratory, in collaboration with two other institutions, are developing the next generation of soil moisture and soil nitrate sensors that are inexpensive, passive, small, and biodegradable. He has co-authored over 100 publications, book chapters, reference journals, articles, extension materials, etc. He has been invited globally to over 30 countries. Professor Hosla, this is written about you, but personally, I think Professor Hosla is one of the most influential personality in the field of precision ag. He's an excellent speaker, and the inception of ISBA was in his hands. So we are looking forward to hearing Professor Hosla. The floor is yours.
Good morning, everyone. Can you hear me? It's a great pleasure for me to be talking to an august group of audience this morning. Thank you so much, Dr. Majumdar, for your kind introduction. I'd like to take this opportunity to thank the chair, Dr. Majumdar, co-chair, Dr. Singh. Also want to express my gratitude to Dr. Praveen Rao, the Vice Chancellor of the University, and my colleague and good friend, Professor Prasad, who was instrumental in bringing this together and inviting me for this presentation. So what I'm going to talk about this morning is scale-independent precision agriculture, a novel paradigm in smart agriculture, and how data will enable future of farming. I'm really excited to be talking to you, and I just want to give you a history that I am not new to the area. I really wish I was in Hyderabad right now, but I'm not. I think as I look back, I left India as a young man about 30 years back. And I remember about 15 years back, my family and I were vacationing in Goa. And I get a phone call from Dr. V.C. Patel. And he said, Professor Hosla, I read your papers and I would like to invite you to join me in a program then for scientists and technologists in the region. And we wrote a proposal, and fortunately that was funded. And so, starting 2007, I started visiting the University of Agricultural Sciences in Raichur. That's where you were the Dean of Agricultural Sciences at that time, to engage in capacity building project. And I spent 4 years of my time there every winter, engaged in research projects. I had the opportunity to visit a number of farms and farmers. I was very impressed with this particular progressive farmer, Mr. Yella Reddy. He is one of the top farmers that I met in that region, and he was already engaged in many elements of smart farming. In 2011, we organized the first Indo-US bilateral workshop on precision agriculture. This was at Punjab Agricultural University. Dr. Manjeet Khan was the then Vice Chancellor. And we had, Mrs. Holly Higgins from US Embassy as a participant to this workshop as well. And we have delegates from many nations around the world. I was very fortunate to be invited in 2012 to be inaugurating the first precision agriculture laboratory at the UAS Whiteshore campus. So, needless to say, I'm not there physically today, but I'm very familiar with the region because I have spent significant time in Andhra Pradesh and Karnataka area in the last 15 years or so. I want to take a moment to recognize a few people, and I know this is an incomplete list. People who have been part of my lab as visiting scholars or postdoctoral fellows, Dr. M.O. Jat, Dr. Professor Adi Narayan from IIT Mumbai, Dr. V.C. Patel, Professor Krishna Reddy, and the list goes on. And this is not even a complete list. And I'm very thankful to all of these individuals who have touched my lab in many ways and went back to India to practice digital or precision agriculture. Let me take you back in time. I don't know how many of you remember 1983. 1983 was a landmark year in the history of humankind. I say so because that was the year when President Ronald Reagan in the United States made global positioning systems an asset available for civil applications. And so a group of friends sitting after a meeting like this started with a question. What if? What if GPS becomes available for agriculture? And what they scribbled on a piece of napkin was later on translated into a schematic put together by Potash and Phosphate Institute at that time. And they had envisioned that at some point in time, looking into the future, that if GPS becomes available for agriculture, all farm operations will be connected to GPS. And of course, this has become a reality in many parts of the world, including on many farms in India. But it didn't really take off. Precision agriculture has gone through a lot of growing pains. It was the year 2000 when the accuracy of GPS was brought down from 100 meters by removal of selective availability down to 15 meters. And I think that was a turning point in the history of GPS and its application in agriculture, what you and I refer to as precision agriculture. And so the founders of precision agriculture cautioned us that when we, as scientists, as farmers, as practitioners, start to practice location-based agriculture, we will be collecting lots and lots and lots of data. And that is what is presented in the bottom half of the slide, showing different data layers of soil tests, potassium, phosphorus, past year's yield map, and so forth. And more recently, I have given many talks in the US and many other parts of the world focused on how do we farm with data? Or a question, how can data feed a growing world? And this has direct relationship with digital agriculture. So before I start talking about farming with data, let me give you a quick refresher on precision agriculture. When I founded the International Society of Precision Agriculture, I designated late Dr. Pierre Robert, professor at the University of Minnesota. He was my good friend and colleague, as the father of precision agriculture. Because it was him in the mid-90s who said precision agriculture is about application of right input at the right time, at the right place, in the right amount, and in the right manner. The 5 R's of precision agriculture. In fact, if you were to go on International Society of Precision Agriculture webpage, you will find the latest definition of precision agriculture. Here's a shorter version that talks about it's a management strategy that account for temporal and spatial variability to improve sustainability of ag production systems. And here's the complete or the more technical version of definition of precision agriculture. I would encourage you, for those who are interested in digital agriculture, to become members of our great society. And notice that this definition is now available in 15 different languages. So if any one of you are interested in translating this technical definition from English into your local language, in Telugu, in Kannada, or in Hindi, or Sanskrit, please contact me. I would really like to have this available in multiple languages. Now I want to draw your attention to one element. This definition that was put together from input by 50 scientists from 30 different countries does not refer to scale in agriculture. The definition is a scale independent. And hence my proposition, scale independent precision agriculture. What do I mean by that? A precision agriculture concept that can be practiced on large-scale farming systems such as this, or in small-scale farming systems such as this. How do we make that happen? Now, my vision suggests for precision agriculture to work, it has to be scale independent. Something that can be practiced in large-scale, medium-scale, and a small-scale farming system. It has to be site-specific. What works in Kansas is not going to work in Karnataka. Or what works in Punjab may not work in Andhra Pradesh. It has to be site-specific. Or what works on one farm may not work on another farm. It has to be locally adapted because there are local cropping systems and agroclimatic conditions that we can't just lift the technology and translate to another place. It has to be operationally feasible because operations vary from farm to farm, from state to state, from nation to nation. And it has to be economically affordable. We cannot come up with a solution that farmers cannot afford, and I'm going to talk more about this. And it has to be socially acceptable. Site-specific, locally adapted, operationally feasible, economically affordable, and socially acceptable. Those 5 elements are very important for precision agriculture, digital agriculture to work in scale-independent environment. Now, the very thing that got us started into precision agriculture was variability. So let me give you an example. This is if you were to fly over Colorado in the United States. You're looking down from the airplane and you see a lot of farms. And as you look on the farms, you see that the fields are not similar. And that's the farm scale variability. I'm going to zoom in on one field, and now you can see that there's variability within the field. And this variability has implications. What do I mean by that? I'm going to click next, and I will show you the plant growing on this field. I'm sure you can notice that as you go from bare soil to crop, the signature of soil is reflected in the crop. And that has a strong meaning for management applications. But as I have learned in my travels around the world, I know at least 15 years back, this question came up multiple times. But there is no variability in small-scale farming systems. Really? And I know this, and I'm sure you all know this too, that there's tremendous amount of variability in small-scale farming systems. This is a variability example coming from a farm field in Zimbabwe, as you can see. Here's a field coming from North China plains. Now, the source of variability may be different in different parts of the world, but there is strong spatial and temporal variability. In fact, in 2007, when we arrived, and I arrived in UAS by shore, that was the first question we had. How large is within field variability? And I had ongoing projects there as well as in China. And we looked at 7 different fields going from 1.5 hectare in size to 7 hectares in size. And our students went out and sampled on a grid basis, just like what we would do here in the United States. And they looked at soil, planting, biomass, grain yield. And then they created the spatial maps. And so you can look at these 7 different fields. You have a variability going from less than 2 tons per hectare to more than 5 tons per hectare, which is 250% spatial scale variability. And when you look at the nitrogen uptake in these plants, now you start to see that there's variability within farm fields and small-scale farming system, as well as across farm field. Something similar to what you and I will observe in Colorado or Kansas and other large-scale farming environments. And there's tremendous amount of spatial autocorrelation. You can see how nitrogen uptake mimics the grain yield. We published this as one of the pioneering paper in the International Journal of Precision Agriculture, documenting for the first time that there's tremendous amount of spatial variability in small-scale farming systems. I'm proud to share this work that was done by Dr. Emil Chia, who was visiting my lab in Colorado, and then back, he did this project. And this is very impressive, because what he demonstrated here is that with precision level, with one intervention, with precision level, and with 50% less irrigation water, they were able to demonstrate that they were able to increase the grain yield by almost 17% and 50% less irrigation water. This is phenomenal. In fact, our work drew the attention of American Society of Agronomy, Crop Science Society of America, and Soil Science Society of America, and they did a cover story on precision agriculture in the developing world, and you can see the picture on the cover page. So let me circle back. How can data be the going forward? Because for people who are engaged in digital agriculture, we know that there's tremendous amount of data that we're collecting these days. So let me share with you nitrogen recommendation and artificial intelligence, a case study. This work has been done in my lab by many young scientists who are working in my lab. So in the United States, in Colorado, Nebraska, Kansas, and I'm sure this is true in India as well, that we have a nitrogen recommendation equation, just like the States. And here's the basic foundation of the equation, that we apply 35 pounds of nitrogen plus for every bushel of expected yield. Bushel is about 56 pounds, or 16 bushels is 1 ton. For every bushel of grain yield, we need 1.2 pounds of nitrogen. Okay? And then we give credit to organic matter in the soil or nitrate present in the soil, or what kind of cropping system we had in the last year, or if there is any nitrate in the water. Okay. So this has been practiced for many decades, how we determine how much nitrogen should be applied in the soil for farmers to grow a successful maize crop. Let me take you to the field. So this is the field that I'm going to talk about. Now, in the traditional farming practice, what we do, we go out to the field and look at the difference in the landscape position, look at the size of the field, and they take 3, 4, 5, or 6 composite soil samples. So the group will go out and take 5 or 6 soil samples. They will send the soil sample for laboratory analysis. The lab will give a laboratory recommendation report, and then farmer will translate that report, depending on how much organic matter, how much nitrate is in the soil, and use this equation to do the calculation. Okay? So the farmer is interested in growing, in this particular example, about 18 tons of maize per hectare, and so he plucked those organic matter and nitrate in the system, and the recommendations say that the farmer should be applying about, if I were to do a quick translation, about 180 kilos of nitrogen per hectare. Okay, very easy to understand that. And so the farmer will go out in the field, load up the sprayer, and apply a uniform application of fertilizer across the field. Now, what happened when precision agriculture started 20, 25 years back? We go back to the same field, and instead of taking only 5 or 6 samples, now we lay a grid because we have the technology to apply variable rate nitrogen using the tractor, variable rate applicator, and so we will go out, and instead of taking 5 or 6 samples, now we will take a lot more soil samples, send it to the lab, get the report, and then based on the report, we'll do a variable rate application. Now, very quickly we learned that if we are going to do precision agriculture, we cannot do these many soil samples because 1, it is time consuming, 2, it is labor intensive, and 3, we don't have enough money to do this. It's cost prohibitive. And so the question was, are there other alternatives? Okay. This is the question we were dealing with, and I remember in 1999, there was funding available from NASA and USDA, and I was among the very few first recipients of $1 million grant to answer this question. Is there a way that we can go out and quantify variability in soils without having to take soil sample? And many of you who have either visited my laboratory or have followed my work know that my lab has done a tremendous amount of work in quantifying spatial variability in soils. We use yield history, we use bare soil imagery, we use topography to translate or quantify variability in soils. In this example, today it's referred to as management zones. So once you have quantified variability in soils, for you to determine how much variability across the zone, you still have to go out and do soil sampling. Now, of course, you're not doing as many soil samples as grid soil sampling, but you still have to go out and do composite soil sampling within each zone. And so then again, there's a question. Is there an alternative? Well, this is the question that my postdoc, Louis Longchamps, started to explore using a fluorescence sensor. Okay? And I'm sure you all realize that harnessing optical characteristics is completely not a new idea. You know, we have been using our own pair of eyes, which are optical sensors, to look at the variability in soils for 100 years, right? So what Louis did, he started using this sensor. Now, this sensor has 3 induction channels, okay? this sensor has 4 induction channels and it has 3 detection channels, okay? So together, when you take reading from the sensor, you get output on 12 channels. 3 times 4, 12. You get output on 12 channels. And the sensor is reading at 450 hertz, meaning if you were to use this sensor for 1 second, you generate 450 data points, okay? Now, because you're getting reading on 12 channels, 450 times 12, you accumulate 5,400 data points. So if you use this sensor for 3 seconds on a soil sample, you can do the math, we're talking about more than 16,000 data points from each soil sample. Here's an example. This is 12 channels, data generated in 3 seconds. And this is only a partial data sheet. This is just 1 sample. And so when you start using the sensor, that means we go out to the same field and start collecting the data by going to the sampling location and using the sensor. This gives you an idea, sampling location 1, 2, 3, 4, 5, 6, right? Now, if this technique works, you have to buy the sensor 1 time, and then you can quantify spatial variability in soils, very similar to sending a sample to the lab. That's the idea, that's the hypothesis. But as you start collecting so much data, then the question is, how do you analyze this data? And how do you visualize this data? Now think about it, this data is an XY scale, right, in XY. And then if you start incorporating soil depth, so that is X, Y, and Z, and depending on how frequently you take the soil sample, then X, Y, and Z and time T. So now you're dealing with multi-dimensional data set. And so because we're collecting so many data points that it is so hard to translate that into something meaningful, we said, hey, can we use artificial intelligence? And so let me give you a very simple example of artificial intelligence. So I said, what could be a good example? Let me start with one of the richest person on the planet, Bill Gates, right? So here are 5 pictures of Bill Gates. You put this picture into the computer says, here's an older gentleman that wear glasses, wear a blue shirt, and a sweater. Okay, I can recognize Bill Gates, Bill Gates, Bill Gates, Bill Gates, but all of a sudden, Bill Gates changes the direction, and he changes the sweater. The computer still recognizes this as a Bill Gates. Okay, it does the interpolation and says, okay, yeah, this person is also Bill Gates. But what happens when there's no sweater? So what I'm trying to do, I'm training the computer using machine learning to make sure it can identify the object of interest repeatedly without human intelligence. So what happens now when Bill Gates put on a tie and a jacket and he starts to turn, look around, what happens now? Will the computer recognize? Well, that requires to train the computer. The computer may not always recognize. And if you have used Google Photos or Apple Photos, you can train the computer to recognize you and your subjects. What happens if it's a younger picture of Bill Gates? Or what happens if it's a very young picture of Bill Gates? Will the computer still recognize? And so what I'm trying to do is I'm trying to train the computer in using artificial intelligence to see if it can help me predict. Now what about this picture? How many of you can recognize this? All of a sudden, this is a very, very young picture, and it's in black and white. What happens now? The computer gets confused. And maybe some of you, I wish I was there in person, some of you recognize that this is not Bill Gates. This is Steve Jobs. You can see the Apple computer. It so happens that at a young age, Steve Jobs and Bill Gates look very similar. So what happens to the computer? Will the computer still recognize the two individuals? This is how we started training the computer, and this is how we're trying to predict. Will the computer still recognize it, or would it be a false positive? And what happens when Bill Gates gets really old? Will the computer still recognize it? So I think this is an example of just trying to express how we're using this technology, machine learning and artificial intelligence in agriculture. Now, soils are, as you can tell, are a lot more challenging because here's a soil sample. This is also a soil sample. This is also a soil sample. Soil sample, soil sample. All these are soil samples. Now, what's the difference? Of course, the color is different, but I'm not trying to determine the color. What my postdoc is trying to do is determine the chemical properties, right? How do we do that? So what Louis Longchamp did, he took the sensor and the GPS unit and the field computer and took the sensor and put it in a bucket so that there's no other source of light energy interfering with the sensor. And then he walked to each and every location in the field. And this is a prototype sensor. So he took a sample right there and took the reading for 3 seconds. So you get the idea. Every time you walk to a sample locations, he's collecting 16,000 data points. Then we also brought the samples into the laboratory. This is one of our undergraduate students, Tani, and Tani did the readings in the laboratory. This is a closer image of the fluorescent sensor on the soil sample. And so to just give you a flavor, these are all the soil samples coming from the same field. Now for human eye, they don't look a whole lot different. But the sensor is trying to determine nitrogen level. So the idea is to use artificial intelligence to quantify, in this particular example, nitrogen. In fact, we're doing work with other elements as well. And so what you see here is a spreadsheet of data. Each row of data is the average of those 16,000 data points that Louis was collecting. And we will call this data set as the predictor. Okay? And then, because we're trying to understand nitrogen, we're trying to understand the relationship between the 12 channels and then the 5 other indices that Louis generated to figure out if any of these channels can use artificial intelligence to estimate nitrogen, or a combination of these channels, or a combination of these indices, and can do the job. So this is called mapping function in higher dimension, because now you're working with 16 dimensions. So you can only imagine that you need a lot of computing power to do this. And so what my other postdoc that I recently hired from IIT Mumbai, he's working in my laboratory. So he started looking at each of these variables, and then he sets a threshold to look at what were the top 5 best predictors or top 3 best predictors. And then he uses 70% of the data to train the model, and then 30% of the data to predict the model. This is work in progress. I just want to give you an example. If we're successful in doing that, could you imagine how easy it would be for us to quantify nutritional capability of numerous parameters in soil without having to, go to the soil, take soil sample, send it to the lab, get the analysis done, get the report done. We can take hundreds of analyses in a very short time. So if we are successful, we're working on this right now. If we are successful, what we can do is we can take an unknown soil sample, use the sensor, figure out the optimum feature selection, train the artificial intelligence model, use the regression analysis to come up with soil estimates to do the nitrogen rate recommendation. That's what we're trying to establish here. One thing I'll tell you is artificial intelligence is only going to be as good as training data that's available. And right now, we don't have a whole lot of training data. I wish I had 10,000 soil samples so that I can train the machine learning algorithms. But once I can do that, we hopefully can do that. One thing I will alert you that you need a very powerful computer and you need a lot of data for training. I'm going to switch gears now. This is a concept model that I have discussed as a concept that could be established in India. I've had numerous discussions with several private partners in India if they would be interested in doing something like this. So this is a small-scale farming system. Just like what we would do on a 100 or 200 acre field, we can pick up a command area, a village, let's say 230 acre village. And if you were to zoom in on those villages, you will find that, the farmers have 1 acre or 2 acre or 3 acre field sizes. In this particular example, 1/3 of an hectare to 2/3 of an hectare, and they're growing rice crop in this example. And in fact, my postdoc mentioned that slowly the soil type layers are becoming available in India as well. It's rarely available in the United States. I know in India, these data layers are not going to be available, but this is as an example, for Krishna district in Andhra Pradesh. Now notice that this data is very coarse. It's 1:50,000 scale, so it's not necessarily good for precision agriculture, but it's a good starting point. And so the idea would be, look at the variability using remote sensing, and then what we would deploy sensors within one field, private partners will deploy these sensor nodes in that village, okay? So let me take you to that village, and again, this is hypothetical, this is a concept, and so you're looking at that village, and the idea would be that the sensor fusion network, which will be solar power sensor fusion network, would be established in different fields in those villages. The data will be collected, sent wirelessly to a nearby base station. That base station, when the connectivity is available, will send the data to a cloud server, and then cloud server will go to intelligence platforms where they will perform the analytics, something similar to what I was talking to you with what we are doing in the lab here in the US. And then that information will be taken to the farmer, and the farmer will actuate that as a decision-making process based on the decision provided by that piece of information. This will be done very similar to the cell phone subscription service, that the information will be available to the farmer on their cell phone. I totally understand that this is not going to be easy. It will require an army of young entrepreneurs. It will require an ecosystem of well-funded agriculture startups. So something this, my new postdoc has been telling me that there are more than 400 startups in India, I'm sure you all know about this, that are working in that space. And close to 2,000 crore Indian rupees have been invested as of June of 2019. In fact, I remember when I was visiting India in 2019, I read this in the newspaper. AgTech to create 2.1 million jobs in Indian agriculture, and that India is launching Uber-like app for farm equipment. So slowly but surely the change is coming, and I think there's a lot of work that has been done by public institutions. I want to recognize the work that has been done by my good friend, Professor Krishna Reddy from IIIT Hyderabad, who really did the brainchild in developing the PJTSAU, and some of this model will be translated, I hope, into private-public partnership to bring solutions to the general public. And this is not going to be new, because something similar service is practiced in many other parts of the world, for example, in Egypt. One thing I want to make it very loud and clear, one, it's not going to be easy. Two, that it requires frugal innovation. It requires frugal innovation because it has to be economically affordable. So nitrogen and water are the two most limiting crop production parameters we all know about water. I'm proud that my lab, along with two other laboratories in the US, are working to develop the next generation of soil moisture and soil nitrate sensors. So this is the current system where it has a tower, solar panel, data logger. This system is expensive. This system is time-consuming. This system is laborious. What we're working on are really tiny sensors that are cheap, very easy, and simple to work with. They have no batteries. In fact, you can spread these sensors in your field, as many sensors as you want, and create an internet of soil moisture or internet of soil nitrate levels. And what we're working on is that after 200 days, these sensors start to fail and they degrade and disappear or dissolve in soil over time. This is a project that's funded by the US government. Our target price of these sensors is less than $1. In fact, if we mass produce these sensors, we think we can produce it for 1 penny. 1 penny would be 1 penny would be 75 hydride. I'm doing the calculation correctly. So the idea is to make these sensors very inexpensive. And there are other groups that are working on sensors that can be pasted on plants. This has been demonstrated by NASA 20 years back, that you can apply sensors on the plant, which is then connected to your cell phone, that will send you the message, hey, give me water, or give me nitrogen. But the central piece of all of this has to be frugal innovation. With that, I would like to end my talk here, and would like to open the floor for questions.
Thank you very much, Raj. As usual, a very captivating presentation, and we see why you are such a celebrity speaker in different parts of the world. May I request Professor Yadvinder Singh to make a few comments?
First of all, on behalf of the congratulate Professor Hosla for an excellent talk, and the new area which has come up for improving the nutrient use of subsidy for precision agriculture, because I think the year 2001 or 2 when NAD became in Rajkot started interacting with Indian scientists like Amateur, and people who came to know about precision agriculture, and we started from using green single plant-based precision agriculture. Now we are going to soil-based, but as rightly said, human resource management is a very important component, because when two people are very, you can say, agitated about precision agriculture, so we still need to go more and more human resource management and a multidisciplinary group with engineers, scientists, agronomists to work together. And I feel that it's a much improved way of agriculture in terms of the lot of information that are in areas to apply fertilizer, vegetable rate of fertilizer applications. And Dr. Alfosa has explained a lot of variations within small fields, and we can analyze how much it will be used.